Okay, what we want to do in this lecture is to find the solution for the state space representation. That's basically if I have a system x dot equal ax plus bu, y equal to cx plus du, okay, given x of 0 and u of t. We'd like to find x of t and y of t. Okay, well, this is basically what we want to do. And in last lecture we said the solution is given by, okay, x of t is given by this equation, which is basically, it has the homogeneous part and the force part. Once you have x, definitely you can get y easily. What is y equal to if I have this x? What's y will be? What do you think y will be? Any suggestion? You just substitute for x. So y is going to be c e to the at x of 0 plus c from 0 to t e to the at minus tau p u of tau d tau plus du. So the problem is in solving the differential equation, not the output equation, algebraic equation. There is not, I mean, it is not that much of difficulty in finding it. The difficulty is finding e to the at. And if you remember, this one again, this requires finding e to the at. And last time again, we said e to the at, we can find it either from the Taylor series, okay, which is a very powerful method. However, the problem with the Taylor series is that, you know, we don't get closed form solution easily. So we go to another alternative. E to the at equal to Laplace inverse of Si minus A inverse. This is what we'll be using. The proof for that one is in the following two slides. I'm not going to go over them because we are a little bit late and it's not important to us. What's important, how do I apply this equation? Okay, so to find e to the at, I will first of all, I'll find Si minus A inverse.
What is A is a matrix?
Yes, A is a matrix. A is a matrix.
Okay.
Okay.
I circle.
Okay. We call e to the at phi of t, or what we call state transition matrix. For the linear time invariant system, they don't, you know, they are the same. If you go to something called time varying system, then they will be a little bit different. The state transition matrix phi is defined as solution for this homogeneous equation with the initial condition phi of 0 equal to the identity. Okay. The solution for the, as I said, the solution, this is, we'll come to this a little bit later, but again, for the state space representation, the solution of the equation is given by this formula, which I already mentioned a little bit earlier. So let me take an example. I have a linear time invariant system, and this is the state space representation. Find y of t for t greater than or equal to 0 if The input is a step function, and this is the initial condition. Okay? So our solution, as we have said, given by this equation. So now, in order for me to find the solution, I must find what's e to the 80. Once I find e to the 80, I can apply this formula. Okay? Now, let me start finding e to the 80. This is the system. So how do I find e to the 80? We said e to the 80 equal Laplace inverse of Si minus A inverse. So what is Si minus A? What does this equal to?
It's S00S
S00S
minus the matrix of the coefficient
which is 0,
variable.
which is
1.
A. This is the A. Okay.
Yes, 0, 1, minus 2, minus 3.
Minus 2, minus 3. Great. Which is equal
Which to S minus 1.
1 minus
2.
Minus 1.
Oh, yes, minus 1. 2 and S plus 3.
2 S plus 3. So this is Si minus A. Any question here? I need now.
How did we get SI, Doctor?
Kev, what do I mean?
How do we get SI?
First of all, S time identity. Since A is 2 by 2 matrix, my identity should be 2 by 2. What's the identity matrix of 2 by 2? Can you tell me? Do you know what's the identity matrix?
Yes, the diagonal should be 1 and the other 0.
You will have 1 along the diagonal for the identity matrix. Since the dimension is 2, so I will have S, and then 0 and 0. This is the identity. Minus the matrix A. And this is my A. This is A, this is B, C, and D. So S times I, this is S times I, and this is the matrix A. Subtract them. How do you subtract matrices?
Okay, I thought S was a matrix, not a constant.
Okay, so this matrices, you subtract matrices, elements by elements. Now I need Si minus A inverse, which is equal to the inverse of this matrix, S minus 1, 2, S plus 3. And how do we invert this matrix?
There's a formula, but you have to find the determinant first, then you do transformation on the matrix itself.
Okay, so because it's 2 by 2, it's very easy. Now the determinant, what is the determinant equal to?
It's S squared plus 3S
S
plus,
times S
2.
plus 3
Plus 2.
plus 2, 1. This is 2 by 2. The inverse, you interchange the diagonal. So this is going to be S plus 3 and S. And this one, you just change the sign. 1 minus 2. This is the inverse. If you multiply this matrix by this matrix, you'll get the identity. Okay? So,
Yes.
inversion. Any question? Now, this is going to be S squared plus 3S plus 2. S plus 3, 1, minus 2, and S. And let me, factorize this one and put it in this format. So I'm going to add S plus 3, okay, S plus 1, S plus 2. 1 over S plus 1, S plus 2 over, and in here I will have minus 2, S plus 1, S plus 2. And finally, this is S plus 1. This is Si minus A inverse. How do I go to the time domain now?
Now we just need to inverse the Laplace transform for each of the elements in that matrix.
Exactly. So basically, we will do the inversion of each term individually. Let me start by the first one, and you will finish. You will do the rest. So I will have in here S plus 1, S plus 2 for this matrix. What is the coefficient of S plus 1? What is the numerator? You eliminate S plus 1 and evaluate at minus 1. So the numerator will give you what? 2. The denominator give you 1. So you are going to have 2. Any question here? And then for the S plus 2, eliminate,
minus 1.
it's going to be minus,
Minus 1.
and so on. So you can finish the rest. Now, tell me what's the inverse of this one?
It's 2e to the power minus t.
E to the t equal to e to power 2
2e
minus t, okay, plus, minus e to power minus 2t. And then you get the rest. Any question here, Shabab? If you do that, this is what you will get. This is your e to the 80. Any question here, Shabab? Any question here? This is coming from the step-by-step, which we have done. Okay? Now, I need, okay, the solution, if you remember, we said the solution is going to be x of t equal e to the at x of 0 plus, okay, e to the at minus tau, okay, b u of tau, b tau. Let me get, so this is the homogeneous part and this is non-homogeneous. Let me get the homogeneous part. How do I get the homogeneous part? X homogeneous. What does this equal to? It's equal this matrix multiplied by the initial condition. And what are the initial conditions? What did you say? The initial condition is given by x to equal 2 and 0. You know what's this transpose? So I must multiply this matrix by the initial condition, which is basically 2 and 0. If I do this multiplication, what do I get? What do I get? What do we get? Multiply this
You
matrix.
get the first column.
What? First
You
column,
get the first column.
which is, no, this is 2. So I'll get 4 e to power minus t minus 4 e to power minus 2t. And then
No, minus 2.
So,
Minus 2 e to the power minus 2.
minus 2, sorry. And then I will have minus 4 e to the power minus t, and then plus 4 e to the power minus 2t. This
Yes, that.
is any question? Okay.
Doctor, can you just repeat what you did again? Sorry.
كيف؟
ممكن تعيد بس ايش سويت مرة ثانية؟ ما فهمت شوي.
What I'm saying is solution حقنا, the homogeneous solution, x homogeneous equal e to the at times x of 0. X of 0 is the initial condition. E to the at is this one. Now my initial condition, the initial condition is given to me 2 and 0. Okay, so multiply this matrix by 2 and 0.
I see. It's just metric multiplication.
Okay.
Doctor, sorry. In the first line, 20xt. Is this 20 part of the first equation or the second equation?
Say that again.
The first line,
أيوة.
the vector next to xt.
Which one?
This one, yes.
This one?
No. The first line.
Yes, this one.
This vector 2 and 0.
2 and 0.
Yes.
This is the initial condition. What I'm saying, if I want to get the homogeneous part, so forget about these. So only e to the at multiply by the initial condition.
This is equal x.
كيف?
This is equal x.
This is what?
Is this equal x homogeneous?
Yes, exactly. Okay,
Okay.
let me clear it. Okay, maybe let me clear it. So this is what I'm saying. This is the homogeneous part. You multiply e to the at by the initial condition, you'll get this equation, which is what we have shown.
Okay, it's clear. Thank you.
Now I need the non-homogeneous. Okay, so the non-homogeneous, okay, okay, the non-homogeneous part basically the non-homogeneous part for x non-homogeneous of t equal the integral from 0 to t, okay, e to the a t minus tau b u of tau d tau. So let me get first of all e to the at from 0 to t. You come in here to the, this is e to the at, replace each t by t minus tau. So that will be what? 2 e to the minus t minus tau. I need t minus tau. So replace from the state transition matrix each t by t minus tau minus e minus 2 t minus tau. And I have minus 2 e to power minus t minus tau plus 2 e to power minus 2 t minus tau. Then I will come in here e to power minus t minus tau minus e to power minus 2 t minus tau. Okay, minus e to power minus t plus sorry, t minus tau plus 2 e to power minus 2t minus tau. This must be multiplied by B, the B matrix. The B matrix, if you remember, this is the B matrix. The B matrix 1 and 1. Multiply by 1 and 1. multiply by the input. Okay. But the input is step function. So what's u of tau in here? What's u of tau? If u is a step function. Shabab, u of t is step function. What is a step function? What is t?
One over x.
What?
1 over s.
Why? Step function. How do you define step function? 0 before time 0 and 1 after time 0. So u of t will be, since I'm going from 0 to t, u of tau will be what? Shabab, step function in time domain. 1. It's just 1.
So
Yes.
you can, so we ignore it, like you say.
Not ignore it, you substitute 1.
No, okay.
Now, okay, let me multiply. This is 1 and 1. So what do? I multiply this term by 1, this term by 1, and put them together.
So it's the summation of the first summation in the
If
first
you
row.
do that, we are going to get what? 3 e to the minus t minus tau. Okay, and then I have in here 1
Minus 2.
is going to
Minus 2.
2 e to power minus t minus tau.
Minus 2t minus tau.
Why? Yes. No. This is
2, no, doctor, 2e to the power minus 2.
wait. No. Add this term to this term. This is 2 and this is 1. So this is 3. And now I have minus 1 and minus 1. This is minus 2. What else you have?
To the power. Doctor, look at the power.
Yeah, the power of minus 2.
Yes, that's what I mean.
Okay. Now the other one, the one down, okay, we will have minus 2, and this is 1 minus 3 e to power minus t minus tau, and then I have 2 in here and 2 in here plus
4.
e to power minus 2 t minus tau. Okay, d tau. And now how do you integrate? How do you integrate matrices?
Term by term.
Term by term. And then since this is definite integral, so substitute in the limits. If you do this process, this is basically what you are going to get. You do simplification, you do this one and add it to this term, this is your final answer. Okay? It is just, I mean, it is pure mathematics, pure math 102.
دكتور,
تفضل.
what if the oh no, I guess late. I only ask at the end of the class. It's better.
I didn't get you.
No, don't mind me. Don't mind me.
Okay. Okay. So this is basically, if you want to solve this, now if I want the output, if I want y, the question is find y. All what you have to do now, this is x of t, y, we said y of t equals c x of t plus du. So this is the C matrix 1 and 0, multiply by this equation, add to it 2, because the D matrix is 2 and U is step function equal to 1, and this is your final solution.
Doctor,
Yes.
the C matrix and the D matrix, how do we like get them?
They are given to you. Look, this is the question. This is the question. A linear time invariant system has the following state space representation. This is the system. So this is your A matrix, and this is B, this is C, and this is D.
No, but I mean, what do they represent in a system? Like, how do we actually get them?
Just 1 second. This is the representation. How do you get what?
Like, if I had a system and I want to get matrix C and matrix D, is that possible or?
Okay. Remember this example? Let me go a little bit forward. Remember this example?
Yes.
Okay. If you go to this example, you put this one in the A, so what is the A matrix? You put it in a matrix format, and that will give you the A and the B. Let me see if I have it before. Okay, look, we have this one, remember? And this is your A matrix, B matrix, okay? And then we said this is the C matrix if the position is if the velocity is your output, and this is if the position is your output. So this is the A, this is the B. It will come either if it's physical system, you can find it. If it is non-physical system, it will be given to you. So you don't have to worry about them. They are given. Either you derive them for the system, or they are given to you. I don't know. Did I answer your question?
Yeah, I understand how I can get them from the equation. It's like,
now let me go back to the property, what we call, of the state transition matrix. Remember, we said the state transition matrix, e to the phi of t, the state transition matrix equal to e to the a t. The property of the state transition matrix, the first property, if I substitute for t equal to 0, I will get an identity. So clearly from here, e of 0 equal to what? E to the 0 times t. Sorry, a times 0, which is e to the 0. And it's matrix, so it's identity. And this is important. When you get your state transition matrix, check if the state transition matrix, is identity or not. If it's not identity, then you are doing a mistake. Let's take this state transition matrix. Now substitute, okay, get phi of 0. Substitute 0 in here for t. What do you get? What do you get?
1 0 0
1 0 0 1. If you don't get this one, it means that you have done a mistake. It doesn't mean if it's satisfied that it is correct, but at least you know you are moving in the right direction.
Doctor,
Yes.
in the previous example, the two inputs was a step function.
The two input is step function. What do you mean the two input? We have one input. Where is two input?
Yeah, so it's not
Example?
This
This example?
Yes.
We have one input. It is single input. It's only you.
Single input. Okay.
Okay. One input.
One input and the two outputs.
One output. Because C equal 1. Okay, 1 and 0. Basically, if you write this equation, this is equal to x. X1 and x2. So this will be 1 0 x1 x2 plus 2u, which is equal, if you multiply, so this is x1, this is 0, there is nothing, plus 2u. So it's only single input, single output. I don't have two output. If the B matrix, if B is a matrix and C is not, I mean, if B is not a column matrix, it's a matrix, and C is not only one row, then you will have matrices and there's no problems. Do it in the same way. Solve it in the same way, it doesn't matter. Okay?
Okay.
Now let me go back to the properties. So this is the first property of the transition matrix. The other property, if I want to invert, remember, if you want to invert a matrix, it's extremely difficult. But if you have state transition matrix, then the inversion process is very simple. Just replace T by minus T. Because look, by definition, okay, P of T equal E to the AT. If I want to invert it, minus 1, which is equal to what? E to the A minus T, which is equal to phi of, okay, minus T. So if I want to invert a state transition matrix, all what I have to do is just replace the T by minus T, which is extremely important property. That's basically, again, imagine you want to invert this matrix. How do you invert this matrix? In normal way, if it's not state transition matrix. You have to find the determinant and then exchange, and so it is not easy. While in here, what we are saying, all what you have to do, okay, the inversion of this one, E to the AT inverse, simply replace each T by minus T. Replace each T by minus T. Okay? So basically what I'm saying is E to the T minus E to the 2T and so on. This is another important property. I don't think we will be using it a lot, but it is, I mean, if you want to go between, in the time domain, if I want to go from T0 to T2, I can go to one point in the middle and do the find my state transition matrix. So decompose your domain into two parts. First part from T0 to T1, then the second part from T1 to T2. Again, if you just apply the definition, you can do it. This is another important one. If I want to raise E to the AT to a K, so basically you replace T by KT. That's basically E to the AT to the K equal to what? E to the A KT, which is equal phi of KT. Again, if you go to what we have, what I'm saying, if you go in here and you want to find, let's say, E to the AT to the power 4, what do you do? What do you do?
You apply the exponent rule.
Which is?
E to the power A 40.
So this is going to be minus 2, 2e to power minus 4t minus e to power minus 8t and so on. And this is minus 2e to the minus 4t, and this is plus 2e to power minus 8t. In here I will have e to power minus 4t, sorry, minus e to power minus 8t, e to power minus t 40, and plus 2e to power minus 8t, which is again very simple. Otherwise you have to multiply it 4 times. Any question? Any question? Okay, let's move to another important topic. Is, remember, we have said we will be having this course the three model: differential equation model, transfer function model, and state space. Suppose I have this system. I would like to use the concept of signal flow graph and convert my differential equation into signal flow graph, and then find the transfer function. That basically I want to go from state space to transfer function. Are they related? Of course, we can get the transfer function in here directly without the state space. But suppose I have the state space representation, how do I find the transfer function here? From V to U. V to U. I would like to use the concept of signal flow graph, okay, to do that. As I said, suppose you have this RLC circuit, and I would like to get the transfer function. This is we already have. If you go to the previous examples, you will have this example is already given. We already derived it by, if you remember, we apply KCL in here and KVL in the other loop, and we get this is the model which we get. Now let me convert this one into signal flow graph. Suppose I would like to convert this differential equation into signal flow graph. Now, how many variables I have? How many variables I have? How many state variables?
Two.
Two. How many? And then I have the input and the output. So let me have, this is my input, U. And I have, let's say, x1, sorry. I will have x2. Okay, let me say this. X2, and this is V. Searchable. Okay. Let me also add, since I have the, sorry, not here, let me add one here. If you have a state variable, let me put the derivative of that state variable as well as a node. So I have x1, let me add x1 dots, and x2 dots. What is the relationship between x1 dot and x1? If I have, this is x1 dot and this is x1.
You multiply it by 1 over s.
So you integrate.
Yes.
For s. This is the same in here. 1 over s. Now, let me change, take this differential equation and put it in the signal flow graph. So x1 dot, which is this one, equal to what? 1 over c u. This is u, so what do I need from it? I take a of 1 over c. What else I need?
Negative feedback from x2.
Okay, so this is minus, okay, 1 over C. Then I need x2 dot, sorry. x2 equal to, okay, what is the gain in this?
1 over L.
1 over L, then,
minus R over L from X.
okay, this is going to be minus R over L. And then I will have, I need V out, which is equal to R times x2. Okay, so this is my signal flow graph. I converted the differential equation into a signal flow graph. Can I find the transfer function now?
Yes, easily.
So basically, this is a neat way of the signal flow graph. So if I want the transfer function from U to V, basically, I will take how many paths between U and V?
1.
1. What's the gain of that path? Okay, the P equal to, what is the gain?
It's 1 over S squared RLC.
Okay, 1 over S, 1 over L, and R, isn't it? 1 over C, 1 over S, 1 over L, 1 over S, R.
Oh, yes, correct.
How many loops I have?
2 loops.
2 loops. So L1, let's say the large one, or the small one. Let's take the small one. So it's going to be L1 equal to minus R over L times 1 over S. This is the one. This is L1. And let's say this is L2. What about L2?
1 over S square. 1 over L.
Square.
1 over L.
1
And
over,
minus 1 over
1
S.
over L. And times
Minus 1 over S.
C.
Over 1 over C.
And minus.
Minus.
Because the minus in here. So the transfer function is going to be, okay, since the path touch all the loops, so delta 1 equal to delta, equal to 1, sorry. And this is your transfer function. So again, to summarize, we have said the 3 model, which I have, differential equation model, transfer function, state space. We have established this relation and this relation. Give me differential equation, take Laplace transform, set the initial condition to 0, give the transfer function. From transfer function, replace each S operator by derivative, and you get differential equation. Now what we have shown in here, how do I go from here to here? We will do more, of course. What we are going to do next lecture is how do we go in this way? What we are going to see, if you go from the state space to transfer function, you have one transfer function. But if you have transfer function, I can get infinitely many state space representation for the same transfer function. So this process in this way is not unique, while this way unique. Okay, so basically what we are trying to do now in here, as I said, work in the 3 models and how do you relate them. And what we are going to do next is, as I said, given the transfer function or the differential equation, how do you find the state space representation. Any question before we stop? If there is no question, then we will stop it here. Thank you very much.
Doctor,
Tafadhal.
the start of this chapter,
Uh-huh.
we found the state space model from differential equation model, right?
If
في البداية يا دكتور.
yes,
state space model من الديفرنشال model.
yes, okay, exactly. In the first example, you are absolutely right. If I have the physical system, okay, then how do I get the state space model? What we gave you an example. What we are going to give you a procedure, systematic way of doing it. Of course, if you have physical system, for example, in here, what we said, I don't have to write the differential equation for the system. I go directly to state space by assuming this is IL is X, let's say this is X2, okay? And this is X1. Yes, we have done that. But what we are going to do, suppose I have this equation. Suppose I have this equation, okay? This is transfer function. How do I find the state space? Find x dot equal ax plus bu. This is what I mean. If I have this transfer function, find the state space. We will do it in a systematic way. You are absolutely right. We have done it at the beginning for the rocket example, for the RLC circuit. You can do it directly. But what we want to do, we want to have, if you have a general equation, a general transfer function, how do you find your state space model? This is what I meant. Okay?
Okay.
Thank you. Any other questions? Okay, شباب.
دكتور بالنسبة للأوفيس أور الحين ولا؟
دقيقة. Let me see. I want to stop recording first.